Alright, so in this video we're going to go over the second traversal, the depth first search traversal. So depth first search traversal is actually more similar to the traversal of trees that is the pre-order traversal. So when you do pre-order traversal with a tree, you walk down the fullest depth of the tree and then you kind of back out and then continue to search as you come back out. And so pre-order traversal is the same as depth first search traversal, and the basic idea is that you want to go as far as you can, and then once you can't go any further, then you back out. And again, the analogy is if you drop something, breadth first search is like you go out in circles, like radially out, and then or concentrically out, I guess is how you'd actually say it. And then depth first would be if you go radially out, so you keep poking as far as you like until you hit the wall, and then you come back, and then until you hit the wall and you come back. So we're going to talk about what the DFS algorithm looks like for graphs. So with graphs you have to be more careful. If you were to write the algorithm similarly to how you write it with trees, you're going to run into problems with cycles right away. So anytime you have a cycle, which you have several in this graph, like the one right here, the just typical recursive kind of pre-order idea isn't going to work because you're going to get stuck in infinite recursion. So depth first search on a graph is that starting at a V, you follow a given path as far as possible before backing up and exploring other paths. So if we start at 1 in this case, this is what DFS at 1 will look like. So we can see that 1 has two different neighbors. It has itself and 0. So it visits 1 first, and then it goes to its neighbor 0. And then it's going to continue on and visit 0's first neighbor as well. So 0's first neighbor is 2, so it goes ahead and goes there. Then it goes ahead and visits 2's first neighbor. So 2's first neighbor that it hasn't visited yet is 7. Then it's going to visit 7's first neighbor, which is 4, and then finally it gets to a point where it can't visit any more neighbors that are new because it's just going to visit itself. So it's going to back up out and go back to 7, and then it's going to visit the next neighbor of 7, which is 8. And then it's done, so it's going to back out and go back to 2. It's done with 2, it's going to back out and go to 0. And now when it's at 0, it can visit 0's next neighbor. So it already visited 2, so now it's going to visit 3 as its next neighbor. And then 3 does have a neighbor, right? It has 4, but we already visited it, so it backs out and doesn't have any more, so it backs out again, and now we're back at 0. So it's visited 0's first neighbor 2, second neighbor 3, now it's going to visit 0's third neighbor, which is 5. Then it's going to continue and visit 5's neighbor, which is 6. When it gets to 6, it has to back out because it doesn't have any more, and it's done. So the order of DFS traversal when you start at 1 for this graph is shown here. So I just went over the algorithm generally with conceptually thinking about how you traverse down a path and then you back out once you have nowhere else to go. And each time you just visit the first neighbor of that node. But how do you actually implement this in the algorithm? So this is what I'm going to be calling the visited vector. It's the order of nodes visited. And so we're going to do it the same thing as we did with BFS. I'll keep track of that in the visited column here. So this visited column is actually the vector that keeps track of the order that it's visited. We also are going to have a stack in this case, and that one's a little bit trickier than the queue in BFS. But we also have the same thing we had before where we have a visited set. So I kept saying, oh, well, we know we're done because we have nowhere else to visit from here. Well, we keep track of that with the visited set. So we are going to go and just start reading the algorithm. So the first thing we do is we set up our stack to include the starting point that we're visiting. So we're going to start at 0 in this case. So 0 is going to be in what's called the frontier stack in this table. So that's already set up right here. And then we're just going to read the algorithm. So the stack is not empty, that's true. So we're going to pop off the stack. So we're going to pop 0 off, and our current v is 0. So far we've visited 0. The neighbors of 0 include 1, 2, 3, and 5. And what we're actually going to be doing here is this is going to be the bottom, and this is going to be the top of the stack. And we're actually going to, right here, I don't know if it's on the slide, right here, this part of the algorithm where it says push each neighbor onto the stack is going to do it in reverse order. So it's going to add the 5 onto the stack first, then the 3, then the 2, and then the 1. So the adding the neighbors to the stack happens in reverse order. Then when we do that, we also add the current v to the visited set. So we've just gone through one iteration of the loop, which is adding the current v to the visited set and adding all of current v's neighbors to the frontier stack in reverse order. Now we're just going to pop off the stack. And so the top of the stack is here at the front, so our current v is going to be 1. So we've now visited 0 and 1, which is there on the graph. All right, so if current v is not in the visited set, which is true, current v is not in the visited set, then we are going to visit it and add it to the set. So now our set is 0, 1, and then we're going to visit all of its neighbors. So 1 has the neighbors of 0 and 1. So it has 2 neighbors, itself and 0. So for each neighbor, we're going to visit each neighbor in reverse order, and we are going to add it to the stack. So we're going to add 1 to the stack and 0 to the stack. So now we are back to a stack that has 0 on it. So we're going to pop 0 off the stack right here at the top of the loop. And so we revisit 0. So here we're checking if current v is not in the visited set, we go in, but 0 is in the visited set, so we actually just skip this whole set, so nothing changes. So our visited stays the same, and then our queue stays the same, and our visited set stays the same. So this was a skipped node. You're going to see that it's going to happen again, right? We're going to pop off the stack again. We're at the top of the loop again, and we are going to now be at 1. Because 1 is already in the visited set, we skip, so everything is going to stay the same. So our visited vector stays the same. Our stack and our set stay the same. Now we go pop off the stack again. So now we're at 2. So 2 is not in the visited set, so we're going to go visit it. So first, we're here, we visited 2, and we're going to add it to the visited set. Now we're going to look at 2's neighbors. So 2 has itself as a neighbor, and it also has 7 as a neighbor. So this loop says push its neighbors onto the stack in reverse order. So we're going to have 5, 3, and then 7, 2. Again, redo the algorithm. So we're going to pop 2 off, and when we pop 2 off, we check, and 2 is, I keep that there, 2 is in the visited set, so that's not true, so this gets skipped again. So our visited vector stays the same, our stack stays the same, and our visited set stays the same. Now we're going to pop 7 off. 7 is new, we haven't visited yet, so we're going to go ahead and visit it. So now we go to 7, and then 7 has 2 neighbors. It has 4 and it has 8 as its neighbors. So we are going to add that to the stack in reverse order, like that. Now we pop off, we go to 4. 4 is also new, we haven't visited it yet, so we're going to visit it. So we add it to our visited vector. We also add it to our visited set. And then we go to its neighbors. So 4's only neighbor is itself. So we are going to add it to the stack in reverse order. And then of course it gets popped off again. So we go to it. We've already been there, so nothing changes. So we will copy down our visited set the same. Our stack is the same, and our visited set is also the same. And we keep going. I'll do one more. So we're going to visit 8. 8 is new, so we are going to go to 8. 8 is going to be something that we haven't visited yet, so we visit. So we're going to add it to our visited vector. We're going to add it to our visited set. And then we're going to visit its neighbors. So 8 doesn't have any neighbors, so it's empty. So nothing changes with the stack. And then you keep going, and you're going to keep doing this until the stack becomes empty, which you can see is going to happen pretty quickly here as we visit our remaining few nodes that are left. And so that is the general idea of how DFS works versus BFS. And the final visited vector for this one, can I write right here? Will it let me? No. So we'll just point it to right here. The final visited, if you want to finish it yourself, is 1, 2, 0, 1, 2, 7, 4, 8, 3, 5, 6, because we started at 1 on the previous slide instead of 0, so it's not exactly the same. So if you keep going, that's what you'll get as your final visited vector, the in order, the traversal order of DFS starting at 0. So as you can see, depth first search uses a stack instead of a queue, and like BFS, both DFS and BFS use a set to avoid cycles. So a little bit of practice that you can go through in order to see if you got the algorithms down. Sometimes you'll need to actually go through the full algorithm, and then for simpler ones you might be able to just do it in your head based off of the general philosophy of the algorithm. So let's do breadth first first. So with the breadth first, if you start at 22, you're going to go to each of its neighbors first. So you're going to go to them in order, 11 first and then 49. And then you're going to go to the first one that you visited its neighbors, which is 11. So that'll go to its neighbors, which are 3 and 19. And then you'll go to 49's neighbors, which will be 35, etc. DFS, if you wanted to do on this particular graph, which looks a lot like a tree, will go down as far as possible before backing up. So in this case, you're going to go to 22, 11, 3, 1. And so that's going to go to the first neighbor of every node, and it will get you to 1. And then it'll back up when it can't go any further, and then it will go to 3's last neighbor, which is 8. And then it will back up, and it will go to 11's last neighbor, which is 19. And then it will back up, and then it will go to 49, 35, and then 30, and then it will back up and go to 61. So with something like this, which is a binary search tree, it's pretty easy to apply DFS because it's pre-order traversal, and then breadth first search is just going through the levels one by one, which is also not bad at all. So this is an example, a quick example of both traversals on a graph that is a binary search tree. That is it.